Hi, this offline video presentation is about to compensate some issues in week number 8 of ele336 microprocessor architecture and programming, which is the first lecture related to x88, 88 and x86 hardware. And we will talk about a few things to refresh our minds related to electronic signals, pin diagrams, integrated circuit connections, and some basic applications, etc. about the chip. And they can be found in the data sheets. Actually, the data sheets are so much complicated, so that this is like a summary of the basic issues for the beginners to use and learn the chip. So let's start with some remarks about some circuit symbols, where the first triangle, unbubbled or dotted triangle represents a buffer when there is one input and one output in the logic systems. Of course, this is not the case in analog electronics, where the triangles usually represent amplifiers. So you have to be cautious about that. Since this is a logic course, we have to think everything in the logic domain system. Besides, the bubbled one refers to inverter, which inverts the logic input. And those devices can be either active high or active low input devices. So any device, especially in the microprocessors or a little bit complex gates or subsystems, the inputs are either active low or high. Where do we understand that? The active low has a bubble. So it's not the same bubble which is after the inverter. So this bubble only represents that this is an active low input, which is activated with the low signal instead of normal high signal. So don't confuse that bubble is not the inverter. The bubble only represents the condition of the output. If it's at the output, it says that this gate is an inverter. If it's at the input, this represents an active low input device. We have to talk about the three-state form. Logic, in ordinary logic, we have two states, either low or high. Three-state is the third one. Actually, it's not the level of voltage state, rather the state of the device which does not represent a low or high signal. Actually, it's transparent device which is insensitive to any signal. So it's electronically connected, but draws or sinks out almost no current, so that it behaves like a very high impedance device. It does not load or alter or change any signal in the circuit. So the first state, so consider the left part is a kind of output to a previous logic state, and which is connected to multiple devices across the bus structure. And the first state could be high. The high is transmitted to both output devices and activates them. In the second state, a low output at the first level sinks the current which is given by the output devices. Now imagine if both of the output devices are connected directly, and if something happens, one of them wants to increase or draws current, whether the other one wants to behave the opposite, so there will be a kind of conflict. It can be burn the device or make an illegal logic function at the bus state. So if we want this not to happen, we have to set some undesired device to a high impedance state, or this is the third state. So it behaves as if it's not connected. So in this particular example, the third state is the device at the left side. So although it's connected electrically, it draws no current, so these two devices at the right side can exchange information via the same logic busbar or the terminals. So when we want to start the hardware of x86, our basic hardware items would be definitely the microprocessor. We have two choices, either 8-bit 8088 or 16-bit 8086. Those are the ancestors of today's microprocessors, where today we can handle up to 32 or 64 bits. But if we learn the basics of 8 or 16, then we can easily manage the powers of 2. The second device, which is necessary for any kind of on-board computer device, is the memory. When especially the memory inside the microprocessor is not enough, we can have so-called external memory to store more information. Our memory chips in this course are rather old ones. They do not exist at this moment. But again, their simple structure and the philosophy, if you learn it, you can definitely extend to today's memory chips as well. 2764 is an erasable and programmable read-only memory device, which has 64 kilobit or 64K capacity, having 6K locations, memory locations, each having a byte of information storage. The next item, 6116, is a 16K capacity RAM, random access memory, where 2K addressing capacity, and each memory location has a byte information storage possibility. The third one is called 61256, is a dynamic RAM, which is 256K capacity for a bit. So the RAMs are special things that you can play single bit at a time if you want to, or you can play with bytes or more. The third item, the third simplest item in the hardware is input and output device. We will learn in week number 9 that input and output can be done either by directly utilizing the microprocessor or utilizing so-called memory mapped. We will learn this in the week number 9 material, but during this overview, we also have a chip. This is an external peripheral chip, 8255, with single addressing and programming the internal flip-flops or memory locations. This is like a 3-port device which can be programmed as input and output easily. So this is a kind of facilitating the I/O procedures of our classical 8086 or 8088 chip. So when we look at some information in the catalogs, so this is a kind of teaching the listener how to read the catalog information. If you look at the chips, the catalog information starts with the title and some most important technical parameters and brief architecture and pin-out diagrams like this one, as you see. So general information is in the upper half and architecture is in the left side is lower half, and the pin-out diagram is at the right side. This is a 40-pin chip, and 8088 and 8086 has almost the same features, but some features are a little bit different. Some pins are multiplex, etc. So there's a, let's say, 20% of difference in general in those two chips. In the catalog information, they are presented in tabular formats, and some assembly coding, etc. are presented. So the catalog, real catalog file is a long file. It's not all reviewed here, but the concepts, you can refer to catalog information if necessary. So this is the very basic diagram. This is our chip in the middle. The biggest rectangle is our 8086. And it should be operational, in operation with the clock signal. And in order to create or produce a reliable and precise clock, another external chip called 8284 can be connected, consisting of an RC timing circuit. Actually, this is a power on reset facility, and the clock circuit is controlled with the crystal, which is a very precision clock generator. And our microprocessor chip is connected to two groups of latches or D flip-flops. Each one has a byte length. For address pins, depending on 16 bits or 8 bits multiplexed forms, we need at least 2, maybe 3 latches to store the information in 20-bit format. So 2 latches, each one having 8 bits or a byte. 2 latches will yield a word of latching, and we need 4 more bits to store 20-bit information as a whole. The other group of latches, actually, they are called transceivers. So they are both transmitters and receivers. So the information can flow in 2 directions. Either the information can flow from outside or peripheral input-output devices towards inside of 8086 memory locations, which is like a receiving mode or reading mode, or the information can flow from memory of internal memory of 8086 to outer the chip, from the microprocessor to the peripherals, which is called transmitting or transmission of the information. Those chips are usually 74245. These are called octal 3-state transceivers or bidirectional couplers. So they are both 3-state chips. So when the data bus connection is not desired, they should be set to 3-state mode, not to influence the operation of any logic circuit subpart in the whole system. So you can refer to previous lecture notes and catalog information and pinning or in the diagrams of, again, catalog pins or your textbook and stuff like that. So any pin can be either input or output, or can be bidirectional. So any pin of the chip can be defined as input. Actually, those are usually factory defined. You don't program the chip pins. You cannot program all the chip pins. Some of them can be input and output depending on the multiplexing of the address and data. So after a brief introduction of the microprocessor, now we can proceed to memory chips. Memory chips are added to the microprocessor to increase the capability of information storage. And if we increase the size of the memory, then we reach out memory banks. So we will consider, after a brief introduction of the solid state of the memory items, here's we see a brief summary of what's inside a memory bank. Each memory bank consists of multiple sections. Those are identical cards or circuit parts, and each part is a kind of either memory chip or group of memory chips in a card. Each memory chip or card contains many number of registers depending on the capacity of the memory. Each register consists of a bit size information, which is actually a D type of flip-flop. So this is a basic flip-flop circuit that you had already learned in Introduction to Logic Circuits. And you remember from that part that each D flip-flop is usually clocked, because that's a clocked circuit. Clocked special connected NAND gates. And each NAND gate is usually a complementary metal oxide semiconductor or TTL type of logic circuit devices. And each semiconductor device actually a kind of physical junction separated, or maybe metal oxide separated physical items. You can refer details of these physical or solid state electronic details in some other courses or books, which is not reviewed here. You are assumed to be familiar with those issues. If you feel that you are not so strong about these issues, please strengthen your skills about those issues before proceeding. And for our course, it's necessary to utilize multiple or identical memory subsystems. What are those kind of systems? Actually, those are some medium scale integrated or very simple logic gates formed with Boolean algebra or Karnaugh map type of things with at least one input and one output. Those chips, those are ordinary chips, start with 74 family and with some character groups to designate their structure, like low power Schottky type of junctions or advanced low power Schottky's or fast type of semiconductor. So many things are different, but the logic functions are all the same, regardless of these letter groups. And this is the unique identifier for any logic device. That 139 is actually 2 input, 4 output, and 1 enable. So actually, literally, we have 3 inputs and 4 outputs. If the enable is not properly set, that device behaves like a 3-state device, does not function, etc. So outputs are usually active low output. So they are high when they are not in operation. When one of them is low, it selects a certain memory bank device or any logic device to operate. And whenever this device is enabled at G bar item, this is an active low input, depending on the selection inputs, one of the 4 outputs, all exclusively, one of them is selected to become low. So this is the truth function of a device at the outputs to designate the active low. So I'm just skipping that step because active low devices have been taught in elsewhere. So actually, this is the logic circuit. This circuit diagram, logic functional truth table of an active low device, and this is the connection. So any decoder This is the simplest decoder. The decoders can have more than these numbers according to their input pins and outputs. This is the simplest and the most smallest decoder, which can control up to 4 memory chips, 27, 64. So actually each one has 64K capacity. 4 of them has 4 times 64 capacity is increased. So if you apply high to the enable, all the outputs are high, none of the memory chips are selected, so they are inoperational. If you apply low to the enable, then this decoder is active, and according to the selection pins of A, B, only one of them, of the outputs, is selected. So this is the particular memory chip which is selected to operate, and this is ready to receive inputs and to yield digital information at its output. So only one of the chip is active. Like this one, enable is low, so decoder is operational, and the selection bits, due to the selection bits high, we select the Y3 output and corresponding memory part. This is the one step further connection diagram. Now, control pins or control wires are as shown with black. Address wires are, or their bus lines actually, are shown in brown. Data lines are shown with green. So the data pins, we have 8. So 1 byte at a time is put in the output, or input can be as well. Well, this is a kind of EPROM, read-only memory, so you cannot write to this device, but if writing were possible, then in and out would be possible. And from which address the data is read to the port is selected by these address pins. There are 13 address pins for these devices, because the capacity of this device is 8K, 8 kilobytes. Actually, the capacity is 64K, but 8 kilobytes information can be selected. So if enable is high at the decoder, none of the chips is active. Whatever the address or data, some other devices are utilizing these information, not these devices are connected to the buses directly. So they are in high impedance state. But when the enable is low for this device, we can select any integrated circuit or memory chip according to the selection pins. In that particular example, enable is low, so this is selected. So selection inputs A, B are low, high. So this is the third, okay, 0, 0 is the first one, and 1, 0 is the okay, B is the least significant bit, 1, 0 is the Y1 output. So this chip is selected. This chip is active, the others are in 3-state mode. According to the address information in the brown, only one of the registers can be selected, and its contents are fed to the output or data bus, which is green. So the importance of 3-state is or can be seen. If we select 2 chips at a time, their information conflict will make the data bus in problematic fashion. So this is another situation, example situation with the high selection, which selects the Y3 output, and we select this register, and the address in that, assuming this is the address of the 13-bit register, these are the bits of these things, and the position of this register in that Chip is in the mid, something in the middle. So addresses start with all zeros and up to all ones, or 1FFF for the 13-bit address. So actually the maximum address is 3 ones and 13 ones means 3 nibbles, 12, and this is the one is the 13th one. Okay, so we cannot have over 1FFF address. So if the address is 013, okay, and the other inputs are like this, you can self-study to estimate the location of the chip in that memory bank special address. Now we can increase the dimension of the control one more. For example, we can add memory read command so that we can read the output of any chip at a certain moment when memory read is low. So this is also an active low input. So this increases the control one step further. And we come to the data bus timing. So for any device, so data bus timing diagrams are like this. So those are the address signals. So there's not only one signal, but many signals on top of each other. So this is a group of signals. Chip select is single signal to enable the chip. So when it's low, actually the chip is in operation in that low moment. Data in means at the data output. So first the chip is selected, then write enable control performed, and after a certain transition period, data is stationary and can be input or output, and then the operation is complete, chip is deselected, and it's connected to as free state. So this is right timing for static RAM. This is not the same as ROM. So this is an example for all kinds of memories, including reading and writing. But previous 2764 is a read-only memory. You cannot write. So the first writing is not valid for ROMs, but the ones next to this argument. So read timing is at the bottom side as well. If we consider a RAM block, now we use 6116 instead of 2764. The decoder and its approach is the same, but we have two controls. We can read as well as we can write to the memory. So reading is made by output enable. Writing is made possible by write enable. The address pins and data pins are as normal. Only the numbers are different. We have 11 address pins for this RAM block due to its lower capacity than 2764 ROM, but the output or data bus width is the same. It's a byte. Again, examples. This is disabled because enable is high. So whatever these signals, forget about everything. So neglect, they are not connected, not in operation. When the enable is low, you can select any RAM like this third one particular. Then according to the address information, etc., if writing and reading are low, any one of them. So if both of them are high, nothing happens to the RAM. Neither reading nor writing occurs, only it waits at a certain moment. If we set memory write low, then we can write to this RAM at a certain moment and to the address which is in the address bus. So the information in the data bus is written into specific that part of the RAM or memory bank. Conversely, if we consider reading, that means the contents of the RAM is copied to the data bus at a certain moment of the clock cycle. Only this RAM part with associated address, and address is assumed to be all zeros, which means the first address at the selection. Okay, so these are good self-study examples as well. Well, I may be a bit quick, but if you self-study in each diagram in detail, then actually this is a very straightforward and algorithmic approach. You can understand very easily, and you can also increase your scale up to gigabytes of memory or many number of banks. All you have to think about is, first of all, enabling, then decoding, then identifying the addresses, etc., and control pins like read and write. That's it. Now, this is an example. Now we increase the number of items in the bank from 4 to 8. So this is the next chip. 138 is 3x8 decoder. So this is a medium scale integrated circuits with a couple of dozens of gates, etc., with a 16 pin package, and its representation is again straightforward with rectangle. Right side are the outputs. Now we have 8 outputs. Left side are inputs. We have 3 enable inputs and 3 selection inputs. Outputs are active low, all active low, but inputs, only 2 of the enable inputs are active low. The other ones are all active high. So okay. Why we have 3 enable inputs? In order to have more versatility in the input approaches. We can control the chip with only one logic signal, setting low or setting high. So we connect any one of them. We can connect with inverters, or we can connect the others in ground or VC accordingly. So we can enable the chip with low signal, or we can enable the chip with high signal, or we can have a combination of 2 different signals at a certain combination, etc., or 3 signals. So that's a powerful device. So we can connect this circuit to a group of address lines as well. Usually the least significant 3 bits are connected to selection pins, and some other pins are connected to the enable pins to define a certain address to activate this, to utilize 8 identical memory parts, like 27, 64. So the rationality is the same. Only one of them is active, the other ones are in steady state. They are all connected to the address buses and address bus and data bus in parallel form, and exclusively one is active, the rest 7 are all in steady state. So this is a truth table of the device, and these, okay, 3 columns, first left 3 columns are enabling pins. So any non-good combination makes the chip disabled, but this 001 combination makes it enabled. So these are, we have some examples. So if this is the enabling combination 001, okay, the chip is selected, and the selection pin selects the Y7 output memory item, and then according to the address pins and data pins, we can again access the information already stored in the ROM. You cannot write information to ROMs, and these are the symbolic address bus and data bus connections. And of course, we can create even more memory chip items, like, okay, this is an example, 4 to 16 decoders with 2 enables. So this is an even larger decoder, 154. Okay, and this is the general circuit schematics of utilizing this chip to be connected to the microprocessor chip. And this chip has 3 latches for the addresses, etc., and data bus transceivers. This is the memory read and write logic circuit, which was explained or will be explained in the I/O devices memory read or write signals. So these 3 signals are from the chip, and these 4 signals are exclusive read and write signals for external memories, as well as input output devices. And finally, this is the 8 and the other 8. So the decoder, actually the decoder is in the previous page. Okay, so these are the 2 enable inputs, 4 selection inputs connected to the addresses, starting from the least significant ones, and it can control 16 memory chips. The 8 one, the 8, okay, group is shown in the first page. The other 8 is here. So this is actually a big diagram in multiple pages. Little bit complex. Don't worry, you don't have to memorize all of them. You won't be responsible that complicated diagrams and circuits in the examinations. So those are the basics of 8-bit systems, including memory expansions, memory increase. But all chips were 8 bits. We can also handle 16-bit memory banks as well. So we double actually chips. Usually, special 16-bit memory items are not produced. They have all started with utilizing 8-bit chips, but utilizing 2 chips one by one. The first one is activated. This is called even bank with the least significant bit 0. So those are even addressed chips. And the other ones are in odd number of addresses. So if you select even, then you activate the first group of 8-bit chips. If you set address least significant bit 1, you select the odd chips. And in order to select that, activate this selection process, a new logic signal BHE or bus high enable signal is also used in the microprocessor as well. So actually it sends signals to the even or odd number of chips to select them. Notice that even bank, the addresses are incremented by 2, 0 from 2 to 4, etc., up to 4 Fs and Es. The same identical chips, but with different addresses, or they are all odd addresses, are selected in the same order, but those are all odd addresses, oddly selected addresses. When we consider both of the chips, 8 plus 8, total 16 bits information can be handled. So in a 16-bit central processing unit, memory locations 5 zeros to 5 Fs are separated into two groups named as odd and even banks. And this is the logic diagram or utilization of bus high enable and A0. A0 is the least significant bit of the address bus. So 0 means the even part and 1 means the odd part. And according to the condition of bus high enable, either you select single bytes or single words at even or odd conditions. So that's a very, let's say, versatile, which is, or which makes possible to run 8-bit or 16-bit codes or programs or information handling for our microprocessors. So to distinguish between odd and even byte, the CPU provides a signal, that BHE signal. It's associated with A0 to decode either single byte or word or double byte memory information. This is a very simplified diagram of utilization, these two banks and their associated transceivers and their logic diagrams, which ones are activated. So since this is rather complex than 8 bits, which includes the, or makes the life a little bit more difficult to handle, only conceptual things are needed or required to be learned at this moment. So if we want to look through simple flow chart of the odd memory bank with BHE, now any memory location in our microprocessor chip, since all the memory locations are byte located, we either write a byte to a byte location or write 2 bytes into 2 consecutive locations, okay? So this is done, okay, this is the normal byte to byte writing. And then after the first 8-bit is written, it's the selection makes to select the next location to write the next byte to complete it to a word. And this is done according to the microprocessor control with the logic signals of BHE and the bank location of, or then parity bank location of A0 address, least significant bit of the address. Our final example includes the dynamic RAMs. Actually, dynamic RAMs are the special type of RAMs which actually are more versatile for the data access as well. And those are special low power RAMs, but they should be refreshed once in a while in the computational cycle. There are a couple of approaches, since RAMs are single bit oriented with columns and rows types of fashion. I mean, the storages are not fixed as byte oriented static RAMs like ROMs or RAMs. They are bitwise and their selection is done according to the column and row-wise fashion. So there's a kind of categorization according to the data access, like standard mode or page mode or static column mode or nibble mode, etc. In 8086, in this course, since we are focusing on 8086 and 8088, we usually don't connect the RAMs directly to them. They were like not too much compatible at the time of their first introduction to the market. DRAMs are more the pieces of memory parts utilized in the later chips. But in order to mention a few items to be familiarized with today's type of memory chips, the standard mode of DRAM has some kind of random access type of operation, and there are registers according to the row or column access modes. Those registers are called RAS and CAS for each cell. In page mode, we have n by n matrix page elements are accessed in sequential order. Static column mode accesses all columns in a row information. So there's no need for column access cycle or register mode. And nibble mode, they're accessed in 4 bits at a time. So there are some information about memory access times and memory cycle times for these, specific for these type of pins. So memory access time is the time interval between the moment that addresses are applied to the memory chip address pins and the time the data is available at the memory's data pins. So they are usually shown in that static bus diagrams are as, sorry about that. Let's check this part. Okay. So the memory access time is actually the time difference between the first selection or some kind of reference point till the data can be read or written. So this is the time lost actually to get that information from the memory in or out of the memory. So you can also have a detailed version of this access mode from the reference point till the data ready to be accessed. So we can conclude that shorter this access time is your faster than your information retrieval or processing. So here's a little diagram of for the interested reader to have even and odd bank structures and some interfacing details if you want to design something like that in the future. And this is a typical, actually a little bit old for today, but one of the first DRAM little cards in the computer motherboard orientation of chips, and their data flow structures are as shown here. So thanks for joining this offline lecture. I hope the information will be useful for you now and throughout your professional career. Take it easy.